And good morning.
Morning.
Sorry for a little delay, but early on, you guys hadn't gotten a chance to get over here, and I'm really glad to see all of you. I'm Frank O'Brien. I'm one of the people who work at XIII. Brad. I just scooted out. One of the things, first off, welcome to VCF. If you haven't been here before, this is a really... If you haven't been here before, this is a lot of fun. You're going to see systems and computing that, well, lots of times, thank goodness we don't use a few of them, and boy, don't we wish we could use them again. One of the great things, and again, it's a shame Evan just scooted out because, of course, he's terribly busy. In absentia, let's give Evan a hand because he's just done. Now, one of the things about VCF is that we celebrate and like to investigate some of the older technologies. We've seen all kinds of great systems. Starting back, when I was young, when some of us were young, the important thing is we were pioneering a lot of early technologies, what today we consider commonplace. But we have a system over at Diana's site. And of course, we'll talk about our speaker in a second. The systems we work on in the vintage world are primitive, awkward, happy if they're character-based. Lots of times it's just switch registers. Oh, here's Evan. Yes, Evan. But that's an important, the idea of having primitive, quote, primitive systems and having that as our expectation, what computing was like in the 60s, 70s, is kind of a misnomer. It was 50 years ago. Think of that, 50 years ago. We went to the moon. That's the most amazing accomplishment in engineering and technology in the world. Think about that. And the computing that was done, yes, there was mainframes and all the rest on the ground, but the computer that took men from the Earth to the moon and back home was small, about a cubic foot, and it was a full-fledged computer system that we think of today as being a modern system. The important thing to remember is that it wasn't a little primitive calculator. We joke that the computer that took men to the moon is no more powerful than my watch or what's in a microwave. That's not true. This was a full-fledged, very sophisticated system, and I will make the argument that it has capabilities that are impressive even by today's standards. This required a tremendous amount of software work. First time in industry, going to the moon and developing software as an important component. A key part of that software development is our speaker, Don Eyles. Yes, this is one of your speakers. A large number of people at MIT and a few contractors worked to develop it. He arguably made the most important contribution, developing the software for the actual landing. He'll be talking about that, and it's a riveting story. Later on, if you get a chance to chat with him, you'll find out about some of his other interests. Art, photography. We can talk all that later. But the important thing is, I'm taking up too much of his time right now. You're not here to listen to me. I'd like to give you Don Eyles.
Well, thanks very much, Frank. That was lovely. And yes, I'm Don Eyles. In a lot of gatherings, I'm sort of a dinosaur. I go back to the days of punch cards and wire wrap and so on. But this is an audience that's interested in all of that. As he said, I did a lot of the programming for the lunar landing phase of the mission, most of it. I am also a little bit of a Forrest Gump or a Zelig in the sense that I was involved in or was very close to a lot of things that happened during Apollo. It was my code that was running on Apollo 11 when the alarms happened. There was also a little known problem, which I'm not going to get into in detail, about the stability of the throttle for the decent engine on Apollo 11 and 12. Going back a little bit, it was my code that sort of messed up the LIM 1 mission. That was the mission in January '68, the first unmanned test of the lunar module in Earth orbit. We had not been told that a decision had been made at the last minute to delay the arming of the descent engine, and as a result, our software, which I had written, concluded that the engine had failed and shut it down. As a result of that, the computer was shut down by mission control, and the rest of the mission was done under ground control. For Apollo 12, where, as you probably know, the goal was to be a pinpoint landing. For that, I helped build in a new capability called Down 69 that allowed navigation data taken at the last minute to be input to the computer to solve the problem on 11, where we were 4 miles away from the landing site when we landed. Apollo 13, of course, didn't involve the landing code at all, but I did happen to be at a briefing shortly before the mission, which was about the time problem that Apollo 11 had and what the possible workarounds would be if it happened on 13. We never had to get into any of that. And as a matter of fact, it was a meeting where I kept quiet because it was bigger wigs than me who were doing the talking. And then on 14, as you may know, there was a problem with the abort switch as we approached the point of lighting the engine for the descent. It was a little bit tricky to work around that, and that one I am going to discuss in some detail today. I hope that will be even down to the level of individual bits, so I hope that will be of interest to you. But first, a little history. And you could say that the story of the Draper Lab, which was originally the instrumentation lab, began here when Doc Draper came across the country with an undergraduate degree from Stanford in psychology and stopped at MIT on his way to Harvard and never left. He compiled the longest transcript anyone ever had at MIT and founded became head of the Aero and Astro department. Only it was under his watch that it became Aero and Astro. It became just the aeronautics department. And formed the instrumentation laboratory, which was the university laboratory that was able to get the contract on a sole source basis for the guidance system, the complete primary guidance system for the Apollo project. That picture was taken on that cross-country trip, and I guess they fed themselves along the way by fishing, among other things. I'm going to skip forward now to the war years of the Second World War, and Doc Draper saw a way of improving anti-aircraft gunnery, which wasn't so much Pearl Harbor as the fact that a few days later, the Repulse and Prince of Wales, the British battleships, were sunk by airplanes in the South China Sea and barely inflicted any losses in return. So it became an acute problem for the Navy, is how to protect ships from airplanes. And he saw a way of using his gyros, and he created, in fact, the Mark 14 gun sight, which is in the upper left of that picture. Basically, there was a mirror in the optical path that was deflected by the gyros such that the aimer would put the sight on the target and it would correct for the lead time, and the lead time due to the motion of the airplane and of the ship. And that's me at about the same age in the other corner of the picture. The big picture is the Battle of Santa Cruz Islands, which was in October 1942. The South Dakota, the battleship South Dakota, had gone to sea with Mark 14s on its 20 millimeter and 40 millimeter anti-aircraft guns, and was able to protect. The battleship is in the background, you can barely see it. It was protecting the carrier Enterprise successfully and shot down 30-odd Japanese planes. The original plane was 32, and Doc Draper stuck with that number, even though I believe the official history say 26. But it was still an epical thing because no ship had ever been able to protect itself before. Skipping ahead again to 1953, the picture is the installation of the Spire, which I believe stands for Space Inertial Reference, what's the E, equipment. It was a three-dimensional IMU, or inertial measurement unit, and that was installed in the airplane, and the airplane then flew across the country to California. It was taking Doc and his team to a conference on self-contained navigation systems. And the air when they got to LA was about 8 miles. There was human control over the engines and over altitude, but in terms of the course, that was done by the automatic system, no computer. At that conference, after listening to several speakers talk about how difficult it would be to do navigate across country with a self-contained system, he strode to the front of the room and announced that he had just done exactly that. It's another one of those moments in laboratory history that's often told. You may not know that MIT had a B-29 bomber, but it did. So far as I know, it never bombed anything. 1957, that's me in high school. And Sputnik, of course, is the big event of that year. And that really set people to thinking at the lab. The people in that picture are Dick Batten, who was, while he lived, the top aerodynamics guy on the planet, and Hal Lanning, who was a big pioneer in computer science. And they wrote a paper called Recoverable Interplanetary Space Probe in 1959 that contained all the elements, including the computer, everything except the crew interface, all the elements that later came into play when we went to the moon. 1961, Yuri Gagarin flew several orbits. Alan Shepard flew a ballistic flight of 15 minutes. And that Shepard's success emboldened Kennedy to announce the goal of landing on the moon within the decade and bringing the guys back, of course. And that started the clock on the Apollo project. I was still in college. I just started college at that point. But I graduated in 1966 and needed a job. And almost by luck, happened into the laboratory at a time when they were hiring anyone and everyone. George Cherry on the left hired me. That's babyface me down below. And I was assigned to work with Alan Klum, whose job was to convert the equations that George had worked out into a practical system. And as we went through the years, I did most of the coding, Alan did some of it, he did most of the analysis, but I think I contributed to that too. That's the building we worked in, fairly nondescript building facing the river in Cambridge. And so we get to the computer. And I'm tempted now, if we have time, to read a chapter from my book, which is about the computer. I believe I have enough light to do it here. First, nomenclature. Generically, it was the Apollo Guidance Computer, or AGC. The ones in the LIM and the command module were identical, except for the software. We usually called ours the LGC, LIM Guidance Computer. As an object, the AGC was a strong-looking, sealed, gold-colored magnesium box, measuring 2 feet by 1 foot by 6 inches, weighing 70 pounds, and consuming 55 watts. It was mounted on the bulkhead at the back of the LIM cabin. Early in the program, North American Aviation, who had manufactured the command module, wanted to know how big the computer would be. No one had any idea yet. Well, just tell them it's a cubic foot, said Dick Batten, and we stuck with that. As an electronic component, the AGC was a single-string machine vital to the mission. It had to be fast enough and have enough memory, but first it had to be reliable. The goal was 100,000 hours without a failure. Reliability would be assured by careful fabrication and testing. Yet, in one of those paradoxes by which technology leaps forward, the only way to meet the goals for speed, weight, and power consumption, not to speak of Batten's 1 cubic foot, was to use a type of component whose reliability at that time was anything but established, the integrated circuit. Eldon Hall, the AGC's principal designer, has written a riveting account of the decision to use ICs. Hall quotes the following doggerel by hardware designer named Jane Partridge. The transistor's a marvelous invention, replaced the tube convention, found its niche to amplify or switch, whatever the designer's intention. But the breakthrough was the IC, integrated monolithically. It became pivotal as computers went digital with increasing complexity. Leaping around here, the upper picture is the circuitry of these ICs that were used in the Apollo computer. There were 2,800 of those in the computer. Inside, well, I'm about to say it from here. I'll skip that paragraph. No one knew where the chips were going to catch on, and there was concern about procurement risk. Not only the computer, but most of the ground support equipment was designed using the same logical type, precisely to create enough demand that the manufacturer would not lose interest in manufacturing it. Ralph Reagan, the program manager, estimated in 1966 that building 4 or 5 prototypes consumed 60% of the country's production of integrated circuits. Conversely, the supplier, aided by Hall's team, could concentrate on perfecting the manufacture of a single type. Every failure was documented and analyzed. New ways of testing were devised. Leaks were detected by weighing the chips before and after bathing them in Freon with enough precision to detect any contaminant that had found its way inside. 10 years before, MIT's Whirlwind had gone through much the same process to perfect the vacuum tube. It was a milestone in computer history when in 1952, Whirlwind achieved 7 consecutive hours of error-free operation. Now, in 1 cubic foot, instead of a 2-story building, we aimed at no errors at all. Chips gone on after all. Today, thousands of Apollo guidance computers can be implemented in a single integrated circuit. In the AGC's read-write memory, erasable memory, RAM in modern terms, information was stored in magnetic donuts called cores that could be energized in either of 2 states, corresponding to 1 and 0. For the fixed memory that contained the programs, a very conservative direction was taken. That's shown in the lower diagram here. A primitive but durable form of memory called core rope. In this case, the ferrous cores acted as transformers, such that a current was induced in any sense line that passed through an energized core. Information was encoded by weaving the sense lines either through or around the cores. To look at, core rope memory was a tangle of thin copper wires. That is why a program that was released from manufacture was called a rope, as in the Apollo 11 rope, revision 99 of Luminary. Ropes were manufactured at Raytheon's plant in Waltham. For the logic designers, the AGC was a computer designed by 2 almost irreconcilable numbers, a word length of 15 usable bits, and a total memory for the Sunburst version that flew on Limb 1 of 34K words. Of that total, 2K was the read-write memory we called erasable, both an operation and the address to which the operation applied. I'll skip over a little bit. Suppose that 3 of the 15 bits were allocated to the operation code. That would be enough to encode 8 different operations. If the remaining 12 bits were allocated to the address, that would be enough to address 4K words of memory. Yet the designers provided for us who wrote the code a rich instruction set of over 30 machine language operations having access to 34K and later 38K words of memory. The dodges by which they did this are an object lesson in draining the cup of ingenuity. For an inexperienced software, it presented a perilous learning curve Its complications were wrapped in solutions and vice versa, until one hardly knew which was which. The designers made a virtue of the necessity that memory be packaged in banks. In other words, there was a bank switching method by which particular banks could be rolled in to occupy certain addresses, as shown in this diagram. As something to be interacted with, the HEC was present throughout the cockpit. Numerous buttons and switches were wired to the computer mode switches for the control system, the throttle, the rendezvous and landing radars, the abort buttons, the ROD switch for controlling rate of descent during the final phase of the landing, and so on. Each crew position had 2 joysticks, a translational hand controller that doubled as a manual throttle, and a rotational hand controller used for maneuvering and also for redesignating the landing site during the visibility phase of the landing. The computer received inputs from both sticks and knew how to interpret them by the positions of the mode switches. In the other direction, the computer gave information back to the crew by means of several ingenious mechanical indicators. The 8-ball, properly the FDAI, to display attitude information, tape meters for altitude and altitude rate, and an instrument called the cross pointers that was used to indicate the spacecraft's horizontal velocity during the final stage of the landing. But there was another place, let me find, there it is. But there was another place where the human interaction with the computer went beyond digital imitations of analog controls and instruments, where the interaction took the form of a grammatical conversation. That was the computer's display and keyboard unit, the DISCI. Rhymes with whiskey. It was an 8 by 8 inch panel located between the 2 astronauts. It had 19 keys, etc., as you can see. The numeric display is, there are also a set of indicator lights. The numeric display is where it gets interesting. At the top were 2 digits that indicated the current program mode, 63 in that illustration. At the bottom were 3 rows of 3 5-digit registers, each with a plus or minus sign, which were our only general purpose way to deliver information. Between the program numbers above and the 3 registers below were indicators, 2 digits each, for verb and noun. Similarly, the keyboard had verb and noun keys. The verb and noun were our language for two-way communication between man and computer. The idea came from Ramon Alonso. It may be cute, but it worked quite well. The set of functions, which we call pinball, handled the mechanics, responding to astronaut inputs on one hand and providing the software with the ability to talk back on the other. Verbs were actions, and nouns designated specific collections of data to be displayed in the registers. For example, to start the landing, for example, to look at any pending alarms, such as we're seeing, well, not in that picture actually, the astronaut would key verb 5, noun 9, enter, and the display of alarm codes would come up. Verb 5 meant display octal, and noun 9 meant alarm codes. Other verbs did not require nouns. To initiate the landing sequence, the LEM pilot would key in verb 37, enter, 63, enter, and that would start program 63, the braking phase of the lunar landing. For the mission planners, the guidance computer was a device capable of performing various functions that could be summed up using the DISCI, ranging from small tasks to large functions such as the programs that conducted the lunar landing. The lunar landing goal of the mission forced a certain progression in the calling of major modes, but there was considerable flexibility in what the LEM or the command module's computer could be asked to do in an off-nominal or worse still contingency situation, or worse still contingency situation for which there was no advanced planning. For the 2 astronauts in the cockpit, the computer was almost a colleague, doing the things it could do best: flying an economical trajectory, controlling altitude, attitude, computing the sequence of maneuvers that led to rendezvous, providing information to the crew and mission control. Well, they did the things the human could do best, such as looking out the window and choosing a landing site. It was not something that happened without training, but with enough rehearsal, the team was harmonious. Flying with them in the simulator at Cape Canaveral, John Young would giggle through the lunar landing about how smart the computer was, by asking for more, of course. Another story for later. From its own point of view, as we were the best qualified to say, the Limb Guide's computer was the almost conscious center of the electronic web. Information came in from keyboard and switches, from which to know the crew's intentions, and from sensors to be chewed and filtered and folded into the plane of information. Jittering forward through time, there was the spacecraft's self-knowledge. To that knowledge, method was applied, and the information that resulted was sent out to displays, to radars, to the ground by radio, and it was acted upon with commands to engines and maneuvering jets. Between the ins and the outs was Sunburst and One Day Luminary, that big block of green bar paper come alive. That was where we came in. We wrote the flight code. The program was a piano roll punched with music we composed, with its characteristic rhythms and polyphonies, but with a melodic line that might sometimes surprise us as the internal logic, based on the immediate situation, selected among the alternate pathways that remained possible. Our computer was a player piano that could improvise. When it flew, our experience would be that of a composer, attending the performance of a work we created, not listening like a member of the audience, but living the music internally. Our life at the AGC was less authentic than that of the neurosurgeon's patient, who experiences his brain from the inside, but it was more intimate than the experience of the surgeon. Using language and logic, we lay down pathways for the computer's inanimate thoughts, and in simulations, we literally trace those thoughts. We did not so much humanize the LGC as assume it as an identity. We thought in code when we were awake, and sometimes we dreamed in code asleep. Let me go back to my pictures. I think I've covered, you can see here the AGC in two views and the DISCI with some information about it. These modules that are plugged into the back of the computer each contained, in modern terms, 12 kilobytes. We didn't think in bytes in those days, we thought in words. So there were the 36K of fixed memory, each one of those modules contained 6,000. There's the web of information I spoke of. I won't go through all of that. And the lower illustration illustrates the core world memory. Now, that's Hugh Blairsmith, who was one of the principal designers of the language. And that diagram, which is from a famous memo called Memo 9, is the best summary of the opcodes, of the different operations the computer was capable of. And if you fully understand that diagram, you know a great deal about the AGC. Down at the bottom there, I've put the link where you can obtain a copy of that. And you will see some actual code very soon. The LIM cockpit, I spoke about some of the things there. You see the 8-ball indicators driven by the computer, the tape meters, the crosshairs, the hand controllers. The left side is the commander's position, who did most of the flying, the stick and rudder flying of the LIM. The LIM pilot, a little bit of a misnomer, stood on the right and had the job of operating the computer and fully understanding the LIM systems. And this is an illustration of how the controls were used during the most intense phase of the landing, which you could say was also the most intense phase of the mission, namely the visibility phase that started about at an altitude of about 7,500 feet, and I believe 4 nautical miles shy of the landing site. The LIM pilot on the right is reading an angle from the DISCI, the LPD angle for landing point designator. That tells the commander where to look on a scale painted on the left window to see the point where the limb would touch down. Part of what the guidance had to do was to keep the landing site in the plane defined by the inner and outer scales, because they were scales on both the inner and outer surface of the limb that, to be accurate, the commander had to keep lined up to get an accurate indication. It was a fairly broad brush way of guiding the limb to a better landing site. And the fine-tuned landing was done in a semi-manual mode that was entered usually at 400 or 500 feet. That's an IBM 026 key punch machine. That's where our hands touch the clay. You may picture monitors on our desks. There was no such thing. I did have a typewriter that I found abandoned and had on my desk, but it wasn't linked to anything. But that was the device used to punch our cards. In the museum here, there's a slightly later model of a punch machine. And I understand that you have an 026 somewhere, but it's not on display. The result of all of this was a book, a lump of paper, about 6 inches thick, and that was enough to contain the entire program. We knew that the solution was in there somewhere, even though it might be complex, and we might not so easily find it, but at least it was all self-contained in a compact place, something that I think no flight computer program now could say. Also in that picture is my personal drink of preference, a copy of Blair's memo and a copy of the coding forms that we sometimes use. And in Cambridge, this was one of the ways we tested the program. On the left is our limb cockpit. The console beside it controlled our visual display that attempted to provide a surface view to the left window. It was not effective. It never really gave us anything useful and was seldom even turned on. The computers that were connected to the simulator, we call this the hybrid simulator because it had both digital and analog computers. And in that lower right picture is a Beckman analog computer. And you see the plug boards by which it was programmed. The AGC itself is in the bottom of the center cabinet in the upper picture. And you see that there's another diskey on the front of that cabinet that mirrored the diskey actually in the cockpit. So if we didn't need the human inputs from the cockpit, we would fly our simulations from that room instead of going upstairs to the cockpit. That's NASA's version. And for it, the digital displays were very effective. They were extremely well done. I flew many landings in that because there were certain things we couldn't simulate using our own capability in Cambridge, which I would travel to the Cape to do. In fact, from Apollo 15 on, I saw every launch, and then used several days following the launch when the crews were no longer needing the simulator to do some final checkout on some of the contingency things that we might need. So I've flown in all hundreds of lunar landings in that simulator. The visual displays originated, well, the simulator itself is that irregular cluster of boxes in the foreground. John Young called it the Great Train Wreck. Behind it, that canopy-like structure contained a plaster model of the lunar surface in the neighborhood of the landing site. And there was a camera that tracked the trajectory of the limb itself such that the picture the camera picked up, put through some processing, was projected outside the windows of the cockpit, which is in the center of that cluster of boxes. In fact, you can see a red carpet and a couple of chairs, and from that point a stairway led up, and then through a door in the back of the limb cockpit one of the jokes was that somebody would come into the limb cockpit and said, take this limb to Cuba. Because these were the days of the hijackings. The first fairly innocent hijackings when the planes were flown to Cuba. So now we get to Apollo 14, and now, if y'all are willing to listen to it, we're going to talk about actual code. I think it's known now as the Apollo 14 hack, the procedure we developed, me taking the lead, that got us around the abort switch short that could have ruined the landing. That's my favorite picture of the Apollo 14 crew there in the lower left. Alan Shepard was flying high at that point, having overcome a medical problem and gotten back to flight status. And the other two crew members were obviously playing second fiddle to him in every way. And those are the abort switches. You can see where they were on the panels. It was the abort switch, not the abort stage switch that had the short. The difference was that abort stage would immediately stage the descent stage, jettison it, and take up the return to orbit using the ascent engine. A plane abort would start the way back up using the descent engine. I wonder if you can even read that. That's too bad, because I would like to explain that in some detail, but that's a page of code. If you bear with me, I'll try to at least summarize what's there. The line numbers were our method of making changes. We could interpolate between lines or replace lines based on the line numbers. These columns here were a method of allowing us to track references to any variable or tag or anything else. A symbol table in the back of the listing would show where the tag or variable was defined by page number, and would also give the page of the last reference, the final reference. And if you went to the final reference, you could then see where it says last and another number. You could then follow it back through to each previous reference until you got where you wanted. The next column is the memory location, and the next column is the, in octal, the number system based on 8. You'll see no 8s or 9s in that picture, except in the line numbers and the page numbers. Shows the actual content of the words of memory that were which you saw in mnemonic form to the right, and on the far right was a comment field that didn't fly, was not functional, but allow us to annotate the code to help people to understand it. The reason I put up this page is that starting here is the aborts monitor, the code that every quarter of a second looked at the abort switches. And that continued onto this page down to about here. And how did we get there? Is that readable? There were two types of program, two entities, two types of entity within the program that we call jobs and tasks. The aborts monitor was in a task that, as I said, ran every 25 centiseconds, meaning every quarter of a second. And the first scheduling of that is shown in the top oval. It was scheduled for the first time from the task that read the accelerometers every 2 seconds, which started the navigation and guidance job. And then it scheduled itself each time 31 centiseconds in the future octal, which is 25 decimal. In fact, the nerd joke in those days was Halloween equals Christmas, because 31 71 equals negative 25. And here, with a lot of the stuff cut away, is the aborts monitor. And I'd like to take you through this in detail. I was told that this audience would be interested in that. If you can't read it, it's going to be a little harder. But the first action is to see if the let abort switch is set, which was a flag word. It was a single bit in a word that was designated as a flag word. And you see that we clear and add the flag word. That's equivalent to fetch. The instruction mnemonics were invented by machine designers, not by software people. So they weren't always obvious. And then we masked that by the let abort bit, which was, I forget exactly which bit, but it was a single bit. And then came the branch on 0 to a fixed location. So if the switch was not set, we would have a 0 there and we would branch. So it was that let abort switch that allowed this monitor to be turned on and off. But there was a catch to that, and that is that at the moment of ignition, the let abort switch was set, because that's the point where we're interested in, whether or not the astronaut commanded an abort. So the fact that we knew before ignition that there was a danger of a short in that switch meant that as soon as the engine was lit, we would be subject to that short circuit. It turned out to be a ball of solder in the switch. And that meant that no matter how fast we tried to reset that bit to turn off this monitor, there would be a period of time, and not only that, a period of time when we had just turned on the engine and there would be some vibration, and we didn't know in which direction that acceleration would make the contamination go. So it was a moment when there was every expectation that there could be an abort before we could have reset it. Not only that, the resetting of it, which was done through the diski, would have had to be hurried. And you really didn't want to hurry diski work, especially if you were reaching into the depths of the memory and changing things. So solving the problem that way was not really viable. So when I learned that we had this problem, the next step, and incidentally, these, I'm quoting this code from Luminary 131, which was the revision that flew Apollo 13. There does not seem to be an extant copy of Luminary 168, which was the code for Apollo 14, but there was no difference in this code, so functionally it serves as an adequate illustration. But what I saw next was that if the mode register was 71, we would not go any further because we thought the abort was already in progress. You see the next test, P71 now, question mark. We clear and subtract the mode register, which means we bring a negative version of that register into memory. We add 71, which was, I believe, 107 octal. And again, if there was 0, if the result was 0, we branch around the rest of the monitor and don't do anything else. So I asked myself, what if we set the mode register to 71? What are the consequences? Well, it would not start the abort. For the abort to actually start, we had to actually go through a different procedure. And so that seemed to be the root of the solution. So that, in fact, was the beginning of the workaround. As we go on, you see, we next see if an abort stage is commanded. If it is, we branch down here to P71, which was started it. And if, but that's relatively irrelevant to the solution of the problem. This shows the place at P63 ignition, the point where the let abort flag is set. And as I say, the fact that set then meant that there was bound to be at least a short period in which we were vulnerable to the abort signal from the bad switch. That's just repeating the aborts monitor for reference. And so the first version of the procedure was that after the countdown started, the countdown towards the PDI, towards the ignition for the landing, after that started, we loaded 71, which was 107 octal, into the mode register, indicating by way of the mode register that the abort was in progress, even though it wasn't. And then after ignition, we would set the reset the let abort switch, the let abort bit, to explicitly turn off the monitor, and then we would restore the mode register to 63, which is where it should be. At that point, we tested it, and it didn't work. The engine didn't throttle up, and the guidance didn't start, and the limb crashed. Unfortunately, somebody sent that procedure to Houston, where they had the same result. But looking at it into it further, we realized that there was one place where the mode register did matter, and that was the scheduling of a task called Zoom. And I'm showing you here the scheduling of that task. The Zoom time, which is the time into the future that we want it to happen, was 26 seconds. So the Zoom task wasn't scheduled. What did the Zoom task do? It did two important things, which I've already suggested. One of them was to make a call to a subroutine called flat out, which would throttle the engine up to its maximum. And the second thing was to set a flag called Zoom flag, which actually activated the guidance, because normally we didn't activate the guidance equation until 26 seconds after ignition. Navigation, of course, was going on, but the guidance itself was not. So the final version of the procedure ended up having 6 steps to set the register to 71, indicating falsely that an abort was in process. And at that point, we did not want to do anything else until past ignition. They could have done some of this during the next 26 seconds, but there was no point in putting them in a position where they had to hurry with the diski. The limb did not maneuver very much at the beginning of the landing, so there was no consequence to delaying the activation of guidance for 15 or even 30 seconds. And we wanted them to be very accurate with these keystrokes, because, as I say, they were reaching in and literally changing bits inside the RAM memory of the computer. So the second part of the procedure was that exactly 26 seconds after ignition, to advance the manual throttle to full, throttling up the engine. The guidance did depend upon starting at full thrust. And after that, we could set another bit to enable the landing guidance equations, and then again to explicitly disable the aborts monitor, and finally to reset the mode register to its proper value of 63, and then finally return the manual throttle to minimum. The reason for that is that if the manual throttle overrode the automatic throttle, the throttle as commanded by the guidance, which was another program I wrote, the throttle control routine. And so if at the point where we regained throttle control late in the braking phase, if the throttle was forced to stay at its maximum by the manual throttle, there would be bad consequences. In fact, if that went on long enough, the limb would literally invert and thrust downwards because it felt it was too high. And that was something that we obviously didn't want to have happen. So that's it. That was the procedure, that was what's now called the hack for the shorted out abort switch. Let's see where I go next. That's Apollo 14 on the surface. We did successfully land, as we all know. Here is the group that was responsible. The core group is that lower picture. At the top, that's Sam Drake, who was one of the experts in the hybrid simulator where we tested it, and Bruce McCoy, who was sort of a middle manager, who was the one that brought me the word about the problem. And in the lower row, Larry Berman, whose main responsibility was the asset, the P12, the normal asset from the surface. But he pitched in and was instrumental during the couple of hours we had to solve this problem. Peter Valenti, who was a rendezvous expert, who also helped, and me. And in the upper picture, I won't go through everyone, but that's me standing next to Doc Draper, who paid a ceremonial visit to congratulate us. That's me being congratulated by Alan Shepard in Houston after the mission. And this might amuse you, although I doubt you can read it. After Apollo 13, Grumman sent to North American, the maker of the command module, sent them a bill based on mileage for the work that the LEM had done to basically save the crew and save the mission. It came to $417,000. In parody of that, after Apollo 14, the lab, my lab sent a bill to Grumman, whose contaminated switch had caused the trouble. And they valued my time at $37. And you see handwritten on there the recommendation to use OEM parts in the future. Okay, I'm about at the end. I'm not sure how I'm doing on time, but
you're good on time.
We got plenty of time? Okay, well, good. We have plenty of time for questions.
How did you know that switch was bad?
There was an indication on the ground. We downlinked over a 2-second cycle. We downlinked 200 values from the computer, and part of that was the indication of the status of the abort switch. So Houston brought it to our attention. If you see the films about the mission, they asked the astronauts to tap on the panel, which they did, which made it temporarily reset, and then it would come back. And so we knew from the beginning that with high probability that what was going on was some sort of contamination inside the switch.
And how much time did you have from determining that till you had to do the fit?
A couple of hours.
Was it tapping on purpose with that, or was that just?
The tapping was to help diagnose the problem.
But I mean, was that functionality? Was that sort of a built-in functionality in the hardware that it would tap?
No, that was just a practical
So
idea.
like hitting the TV.
That's not, yeah, it's like,
I see.
yes.
So with the setting of the mode register, that was done through the diskey?
Yes.
But it sounds like this mode register had other bits which were being set by other tasks or something like that.
Yes.
So if someone, we now call it a race condition, if someone sort of modified it in the diskey, wasn't there the chance of sort of the values being overwritten again by?
No, we knew when they were written.
We knew.
And they were really only written when the program began.
And there's a follow-up question. So how exactly were these separate tasks running? Was there hardware which was sort of building up the preemption?
Yes, there were hardware interrupts, and one of those interrupts could be programmed to occur at some point in the future, and there was software that regulated that. And so that's how tasks were scheduled, with a centisecond granularity, 100th of a second granularity.
John,
Yes.
did you figure out what caused it short and what doesn't prevent it in the future?
Say that again?
Did they figure out what caused the short, what was done to prevent it for the next
It
one?
was the contaminated switch, and in fact, we installed a systematic way of overriding bits that came from switches for the next mission and so on.
How did you actually communicate that patch? Did they have to type it in, or was it,
Yes.
did you send it from ground?
It was, yes, I mean, we wrote it down, we read it to Houston, made sure they had it right, they read it to the crew,
And they
and
typed
made sure they had it right, and so the crew did it on board through the disk.
Yeah, I thought it was Apollo 11 had an abort switch problem also,
It
didn't
was
they?
14.
No, 14.
Apollo 11 had a different kind of problem. It's all in here. Do we have time for more?
Sure, 5 minutes.
What was the interface between the diskey and the computer? Was it memory mapped for the switches, or was it a serial connection of some kind? Do you know?
I don't think memory map would be the right
No.
word. I'm not totally sure about that.
I know that multiple diskies could be connected to one machine, so there was some kind of interface.
There was certainly an interface. There was a fairly large block of code, I think a couple of thousand words, called, loosely speaking, pinball,
Oh, okay.
that looked at those inputs and made sense of them.
I'll look it up.
I'm not quite sure how they happened. I think there was an interrupt that happened whenever a key was pushed,
Ah,
which told the software what key was pushed, and that was kept track of.
The software itself couldn't be changed in flight, it was only burned and ROM on ground.
It was in the form of this core world memory that I spoke of, which was hardwired. I mean, software is a little bit of a misnomer, because that had to be wired. We had to give at least 6 weeks lead time before the mission to have those ropes manufactured. And there were a few cases where there had to be re-releases as things came up between the original release, and even individual modules were sometimes remanufactured. In the back?
So the switches were all just a single contact?
On the diskey?
Yeah, no, well, the abort switch.
Well, the abort switch was.
Did they ever change that to like a dual contact or like confirmation or?
The switches were never changed. There was never a hardware change. There?
Yes, what would they do if they did need to have an abort?
They could do it through the diskey.
There was a separate command sequence for that.
Yes, exactly. You could, the same standard sequence you could use to select any program, you could also select the abort.
Instead of direct access, just with one button.
Instead of the single button, yeah.
It would just take longer.
It would take longer.
Okay.
So there was maybe some slight hazard if something very bad was happening. It might take a few seconds to select the abort. Yeah.
It seems that the project recognized early that an analog computer would not be adequate because you had this very ambitious use of ICs and so on, and the rope, and in this period of time to build that aggressive technology. What requirements would have been most difficult to meet had an analog computer been considered for the vendor?
Well, that's a good question. I'm not sure I'm so well qualified to answer it. I think that because of the wide variety of functions that had to be upcallable, that it was realized early on that you really needed a digital computer. It was one of the things when I mentioned Hal Lanning and Dick Batten, I think that was one of the things that they may have discussed in that paper I cited.
Don?
Yes.
So what were your lessons learned advice be for today's programmers?
In a general sense, I would say that the main lesson was intellectual honesty with ourselves, to not underestimate anything, to get to the bottom of any odd phenomenon we ever saw and not just explain it away, as was done, for example, with the Hubble mirrors, where there were indications that there was something wrong, but it was explained away instead of gotten to the bottom of it. The lessons of the abort to have overrides for anything coming from a mechanical switch, for sure. That was the lesson we learned immediately. More generally than that, I'm not sure.
Can you talk for a few minutes about where your career went after this?
I stayed in the manned space flight business. My lab had been able to get the Apollo contract for the guidance system over the protests of certain companies. There's an interesting story, actually, that I believe it was Bell Labs who at one point came to Cambridge to question us. And Dick Batten was running that meeting, and it was summertime, and the windows were open, and there was a fly buzzing around the room. And at one point in the meeting, Batten was idly playing with a pair of scissors, and as the fly went past, he did that. And the fly fell on the table in 2 pieces. Wow! And that sort of quieted the meeting. For shuttle, we never had a chance to have the guidance system contract. And so during the shuttle era, what I worked on and what we tended to work on was simulations. We had several different simulations. There was one called the integrated package that I wrote a lot of ADA code for, which was essentially to actually program a lot of the software that was needed according to the requirements. The goal was to verify the requirements, but that was non-flight code. There was also a simulation called the OFS, the on-orbit flight simulation. And to lead into the next phase, one of the things that I developed for that was a paper pilot, if you will, sort of capability. And instead of being a time tag list of commands, this was a capability that could actually make decisions based on a wide range of data from the guidance system, and then input commands, including the astronaut keystrokes, but also reaching into memory, also calling in some diagnostic programs. It was called Timeliner, and it was basically a language built around concepts like when, whenever, before, until, with all the bells and whistles that went with that. For example, there could be parallel strings of logic. So you could have a simple one that said, whenever such and such do this, while some other sequential string is running in parallel with it. And that was in the early 80s. 10 years later, when the space station was being first designed, we realized that what Timeliner provided was very much, had a great deal in common with what NASA wanted for what's called the user interface language for the space station, UIL. And in fact, then it was sort of the second exciting period of my career in space flight. We attempted to sell that to NASA as the UIL, and that took, instead of 2 hours, that took 2 years. But we got the flight controllers on our side, we got the payload folks in Huntsville on our side, and we were competing with a much simpler time tag command system proposed by IBM, which was going to be both a lot less capable and a lot more expensive. That culminated in a meeting in Houston, which was a little bit like a reunion. It was Dick Thorson, who had been a flight controller for the guidance system during the Apollo 14 crisis, and was chairing the meeting as the head then of the software control board. And Gene Kranz was at the meeting. In fact, he came to the meeting and sat right behind Thorson, and he had a fork in his breast pocket, a metal fork from the lunchroom with the points pointed up. And I never knew whether that was like an old-fashioned court-martial where you knew by which direction the sword was pointing. But I noticed it. And the rest of the room was filled with the younger flight control people and some of the payload people who were on our And in fact, after asking a couple of tough questions, it was approved. And that was in '92. And so between '92 and '98, when I retired from that, we were working to adapt Timeliner to the space station systems and provide the ability, a big part of that was to provide the displays that allowed the astronauts to monitor what it was doing.
I have one last question.
Yes.
Do you have any brief thoughts on today's private spaceflight industry?
I'm all for it. I believe that Obama, when he came into office, had a difficult situation because a lot of promises and proposals have been made by Bush without any backup, without any real support. And I believe it probably was the right time to turn the job of providing access to low Earth orbit over to private companies. And I think we'll see the benefit of that in another few years. While NASA, to allow NASA to concentrate on deeper space missions.
Any last questions for Don? We have time for like one more, but he'll be doing a book signing later. We have time to talk to him. One more question. Make it a good one.
So were you watching the lunar landing on Apollo 11 live when the 1201, 1202 alarms were happening? And what was your reaction? And what went through your head?
I was terrified. I mean, there was something happening in the computer that we didn't understand at all. NASA had the advantage of us there because, as has been written, there had been a problem during a simulation when one of the other impossible alarms had happened, and Gene Kranz had demanded a thorough analysis of all the different alarm codes, and they had looked at the 1201 and 1202 alarms and had seen that the spacecraft can still fly with those alarms. And so they had a better perspective on it than we did. And as a result of that, they said, okay, let's continue until there's some further sign of problems. And as you may know, there were actually 5 different instances of those alarms. In one case, the diskey was blank for about 10 seconds. I was out at the debriefing and someone asked Neil, what did you think when the diskey went blank? And he laughed and said, we thought it was never going to come back. But they kept flying, and they have my admiration for doing that. I probably would have pushed the abort button, the non-contaminated abort button.
We're going to have some announcements first at the ground floor.
Questions, and as Evan said, I think at noon we're going to settle somewhere.
I'll make something else.